Hello and welcome to the Daily Space for Thursday, July 12th, 2018. I'm your host, Dr. Andres Plazas, and as always, we're going to bring you a roundup of today's news from space and astronomy. So today, we're going to start with some exciting news from neutrinos from outer space. So, Today, the National Science Foundation had a press conference, and it had to do with cosmic rays and neutrinos. So usually we get signals most of the time, a lot of signals that we detect here from the sky. We call them cosmic rays, and these are high energy particles that they originate from far beyond our galaxies. And sometimes we have been able to identify the sources of these particles, but for many instances we actually don't know where actually they come from. But today, the Ice Cube collaboration, they said that on September 22nd of last year, they detected an ultra high energy neutrino, just one hit, that arrived at the South Pole telescope, and then they said at the South Pole, I'm sorry, and they said that they were able to identify their source. So these are big news because this signal was confirmed by a series of gamma ray telescopes, and they say that the source of this high energy neutrino is what is called a blazar. We're gonna define it in a few seconds. And so we know about neutrinos. These are these tiny particles from the standard model of particles physics that they don't have any charge, and they were discovered and introduced in the 30s, in the 1930s. And in 1956, we actually detected them when we put detectors outside of nuclear reactors, and then in the 60s we were able to build larger detectors and find solar neutrinos. But then it was in 1987 that we were able to find neutrinos coming from a supernovae, so neutrinos coming from out of the solar system. So that was a big deal because historically mm, this marks what we know as the origin of multi-messenger astronomy, because we saw a signal from the sky that came from neutrinos, but at the same time we were able to identify an electromagnetic part, the counterpart as an electromagnetic part, and that was the supernovae. And then for about another 30 years, these neutrinos from the supernovae were the only neutrinos that we had ever confirmed to come from the solar system. That didn't mean that not we were not receiving more distant neutrinos. It just meant that we were not able to confirm the origin of these neutrinos, sort of these cosmic rays, high energy cosmic rays. Then enter the Ice Cube detector, and the Ice Cube neutrino detector is designed to find the signal of those neutrinos that are they don't they're very hard to detect. But this Ice Cube detector consists of about 5,000 light sensing detectors arranged in a giant three-dimensional grid of ice in the South Pole. And then when a neutrino collides with an ice molecule, it's a very rare event, but it happens. Um, so the neutrino collides with an ice molecule, and then it creates what another particle that is called a muon that radiates a cone of bluish light. It's a cone of blue light that is called the Cherenkov radiation as it propagates through the ice. So it's like an electromagnetic shock wave going through the ice, and then you are able to identify this light with the detectors. And because of the shape of the signal, this conical shape, we are also we are also able to identify the incoming trajectory of the neutrinos. So as I said, the Ice Cube detector on September of last year detected one of these events, and then at the same time, within 43 seconds of detecting this event, they released an alert. They sent an email to a bunch of reds of a bunch of another net of telescopes around the world. So this is similar to what happened with the discovery of gravitational waves and an electromagnetic counterpart. And yes, so but in addition to saying that they had found that they have identified this very high neutrino, about 100 tera electron volts, which is about like 10 times more energetic than whatever you can produce in the LHC. So they said that they found that event, but at the same time they were able to identify the coordinates of where that event came from within about 1 square degree of the sky, which is a more or less large region, but it's a region that you can actually look if you tile the sky with enough patience, and then you're able to try to figure out if you see something else at the same time. So then a bunch of other telescopes, gamma ray telescopes, were able to identify another source, and then in the end, scientists determined that the origin of this high energy neutrino is what is called a blazar. A blazar is a supermassive black hole that is currently in an active state and is feeding on matter and accelerating into very, very high speeds. So a blazar is like a quasar, but there is one important difference. In a quasar, you have with your black hole, and you have your accretion disk, and then you have two jets coming from the axis. And a quasar can be oriented in any direction, but a blazar, by definition, is pointing. It has its jets pointing towards the Earth. So they had this name as blazar because they blaze right at the Earth. As I said, a bunch of other observatories were able to detect the signal from this object. One of them, it was the Large Array Telescope on board of the NASA's Fermi Observatory, the Fermi-LAT Observatory, but also ground-based telescopes, such as one called the MAGIC Telescope in the Canary Islands. And here we can see a map of the network of detectors around the world that were able to also to identify the signal from this object. So by combining these neutrino observations with the electromagnetic ones, we have been able to establish in a robust way that these high energy neutrinos were indeed produced by these blazars, and that we have the capability of detecting them, and even at such a great distance. And then they found that this object is at about 4 billion light years away. So we can learn a lot about this type of observation. This is just the beginning of what we call the multi-messenger era of neutrinos and electromagnetic waves. But obviously, one of the things that we have learned is that we have demonstrated that blazars at least one source of cosmic rays. So as I mentioned at the beginning, we have been receiving all these cosmic rays from throughout the years, but we're not sure actually where they come from. But now we know that at least one of these sources, we have confirmed that is this type of quasar that we call blazar. Another more technical thing that we have learned is that to produce neutrinos, you actually need something. You need to have the decay of another particle called a pion, and these pions are actually produced when you accelerate protons. So this actually is giving us the first evidence that we have proton acceleration by black holes. We have demonstrated with this observation that this particular blazar is one of the most luminous sources in the universe, because being of such a large distance from us. And we have say, of course, that cosmic neutrinos and cosmic rays have sometimes at least a common origin. So we can definitely say that the era of multi-messenger astronomy is here. So today at the press conference by the National Science Foundation, the director Franz Cordova actually was saying, and I'm gonna quote, that the era of multi-messenger astrophysics is here, each messenger from electromagnetic radiation, gravitational waves, and now neutrinos gives us a more complete understanding of the universe and the important new insights into the most powerful objects and events in the sky. Such breakthroughs are only possible through a long term commitment to fundamental research and investment in superb research facilities. And this was said by the director of the NSF, Franz Cordova, and I wanted to highlight this last sentence that is something similar to what happened with the detection of gravitational waves that we spent literally like decades, 40 years, working hard on these detectors, and in the end, the payoff was huge. So sometimes of course, the reward is not immediate, but as we have learned historically in science, if we're patient, probably we're gonna have a breakthrough sooner or later. And this is one of the most exciting news of the days. And then I also have two stories related um, to the Gaia mission. So changing topics a little bit. Um, a team of scientists from Georgia State University have actually used the Gaia mission to revisit what we call the HR diagrams of stars. So, what is an HR diagram? It's a Hertzsprung-Russell diagram. It was invented by these two scientists in Denmark about 100 years ago, and it's just a diagram where you plot the spectral classification of stars in one axis, or the temperature in the lower axis, as a function of the luminosity of the star in the y-axis, in the vertical axis. And this is basically a scatter plot. And by doing this kind of plot, the cool thing is that you don't see that the stars populate like all the regions of this diagram. You actually find a certain locuses or certain geometric regions where the stars tend to be. And then actually with years we realized that this type of diagram was telling us about the stellar evolution of these objects. So this is as I said, the resulting position of the stars on the HR diagram. They reveal a distinct stellar evolution stages, and also tells us about the different stellar populations that we can have in this diagram. So the main line of the diagram is what is called the main sequence, actually, and the sun is actually lying at the center of this main sequence. It's showing us that is one of we can locate the different type of stars on these diagrams. But now today, so we've been doing all this type of diagrams, and it's been very useful to classify stars and to tell us about the stellar evolution throughout all these years. But now today we have a superb set of positions and locations of stars by Gaia. So we are in the era of what we call the era of precision astrometry. And recently in April, the Gaia mission has released what is called a second data release. And these scientists actually have explored again these diagrams, have revisited this diagram, and they have discovered a surprise that there is a gap in the HR diagram in the point where a certain type of stars called M dwarfs are located. So you find like an underrepresentation of underpopulation of stars in the diagram. So it's a subtle effect. So here you can see the actual plot from the paper, and this is a zoom in from a main sequence part of the HR diagram, this plot that you find on the left. And the blue part of the region is actually telling us that that part is underpopulated. So as you can see, it's very subtle, and then you can think, okay, why do we care? But actually, this is telling us that there might be something going on, that there might be like a physical process behind that behavior in this underpopulation of this particular part of the HR diagram. So in the article that the author submitted, they do a lot, of course, of error checking, and they check that they see this underpopulation in different color bands, with different types of analysis, and they are able to reproduce this gap, what they called in this other type of maps that they do. So this is telling us that this is a robust measurement that is not actually like a mistake in the measuring the colors of the stars, or something in the instrument or something like that. Every time you publish one of these scientific analysis, of course, half of your paper is gonna go into explaining people why you are sure that you understand the errors that came in through your paper, your random errors or your systematic errors. So the authors they argue that the presence and persistence of the gap, it suggests that it's due to some underlying physics that they haven't yet thought of, but they have an idea. They suggest that the gap may be related to a non-transition in this type of stars, in these M dwarfs, mid M dwarfs, from the transitioning from larger stars that are mostly convective, in which energy is transmitted through convection, and they're doing a transition to smaller stars that are fully convective. So they're doing a transition from stars that are partially convective to stars that are fully convective. And the authors propose that the missing stars in the gap may be due to subtle changes in the structure that occur at this transition between partial and full convection in this type of M dwarfs. So in the future, the authors they propose, of course, to gather more data, like look at other parameters, for example, dynamical masses, dynamical sizes of the stars, metallicities, rotational periods, even magnetic properties, and then on the type of stars that are close to this gap. And they hope that by getting more parameters, more physical parameters, you are able to see more trends once you have expanded your parameter space, which makes sense. So yeah, I thought that this was also a very interesting story that is telling us about how, every few weeks, I keep finding a new story about how researchers have been able to find, or to refine, or to improve our knowledge, thanks to the Gaia catalog. And this leads us actually to the last story of the day, which in which actually researchers, this is a story about cosmology, but now researchers have used the power of the Hubble Space Telescope. We know it's one of the most powerful optical telescopes that we have, even after like 30 years or so, it's still going steady and strong. But they have used data from the Hubble telescope, and they have used data from the Gaia mission, again, from the improved parallaxes or positions that the Gaia mission is giving us, to give us an estimate of the expansion rate of the universe. So this is a topic that we have touched in the past here in the daily space, and in particular we're talking about the Hubble parameter, or referred to as the Hubble constant, which is basically telling us the expansion rate of the universe. So the underlying problem here is that, and I believe that I have said this before a couple of times, is that okay, so we have discovered that the universe is expanding. This happened about 100 years ago. Edwin Hubble and others found that all galaxies tend to move farther away from each other, and then you can measure that rate of expansion. And then nowadays we can actually measure that rate of expansion directly in our local universe. If you identify stars in other galaxies that have particular properties, these are called the Cepheids, that they actually change in time. Their brightness changes with time. You are able to identify this type of stars, and then you can have a direct measurement of the expansion rate of the universe. from a local point of view. But at the same time, we also have the cosmic microwave background, which is telling us about how the universe was about 400,000 years after the Big Bang. And then from there, you can also have a measurement of this Hubble parameter, of this Hubble constant, Hubble expansion rate of the universe. And nowadays, there is a tension that keeps growing and growing, and the conclusion of this study that these authors have put forth is that the tension is still there. So as time goes by and we get better and better measurements, if we keep seeing this tension, because this could actually point to very um, differences in the fundamental understanding of the standard cosmological model that we have, because this shouldn't pass. So actually, the leader of this investigation of this result is um, Adam Rees, who actually got the Nobel Prize in 2011 with other scientists because he measured the accelerated expansion of the universe and dark energy. But here we're talking about the standard expansion of the universe, the Hubble parameter. And Dr. Rees actually says when in the press release that the discrepancy is like if you predict how tall a child would become from a growth chart, like that's the CMB, and then you find out that the adult has actually greatly exceeded the prediction. So that's why we are very perplexed. And the prediction is the actual you compare the prediction to the local measurements of the expansion rate of the universe. So the key difference here is that Gaia actually is giving us a precision that allows us to measure this the expansion rate of the universe from local measurements to 2%. And the goal of Dr. Rees's team is to keep working with Gaia and to keep improving this precision. And they actually have the goal to bring it down to even 1% of error of precision. So I was talking you about errors in the previous story. So now the name of the game now is, if we want to know that this tension is real, we need to be able to understand very well our random errors, our systematic errors, and even more, we should be able to shrink the error bars in such a way that the measurement from the CMB and the measurement of the local expansion rate of the universe are comparables in terms of the error bars, and that error bar is of about 1%. So yeah, this is a result that was published today on the Astrophysical Journal, and which I find very interesting because I'm really curious to see if this tension is actually there. And from the cosmological point of view, we're waiting for surveys like the Direct Energy Survey to finish its 5 years of data. This is gonna happen actually DES already finished the 5 years of data, but the analysis is gonna be released in the next 2 years. But then there are other surveys and telescopes such as the LSST, the Large Synoptic Survey Telescope, that will come in 2021. And these are going to be even larger data sets with more precisions that are going to be able to tell us if this tension is there or not. So that's all for today. Thank you very much. And I'm going to check now the chat and see what comments you guys have. Hello, Guido, keeper of maps, Renistro. Cherenkov radiation. Yeah, thank you for putting a link on that. Hannes Vorwerp. Super Kamiokande, yes, that was another one, the Japanese one, another of the observatories that was able to measure the signal. I had no idea that neutrinos could get to such high energy levels. Yes, that's actually pretty cool. Yeah, it's very exciting. This is one of the most exciting parts of the news, that because usually then of course you have an energy distribution, and these type of events that we're talking about, they actually lie at the very tail of the distribution, and that's why we only have like an order of few events of with this type of energy. I wonder if the amount of quasars that have a probability of pointing at us matches a lot of the cosmic rays we didn't know the origin of. Yeah, that could be an option. Yeah, could be something that could be calculated, I suppose. But yeah. So, okay. Does that mean that there are, so this is related to the second story that we're talking about. Does that mean that the stars that cannot that there are stars that cannot exist because their convective motion is not allowed? Um, that's yeah, I don't have the exact answer to that, but I'm thinking that yeah, I mean there has to be like a physical process that allows you to first. Usually you have these convective motions in these small stars, these M dwarf stars, and then what these researchers are talking about in this particular story, or this particular paper that they wrote, is that maybe the gap that they see in this HR diagram, it comes from the transition of coming from this convective phase to like a partially convective phase to a fully convective phase. But then yeah, are there stars that do not have at all any convective motion? Yeah, you can also transfer energy by radiation or other means, but I don't know if there are not actually like stars that cannot exist because convective motion is not allowed. But yeah, so yeah, if I had a band, I would call it H not tension. That's a good name for a band. Yeah, the Hubble tension. Did they say there was a difference between the expansion rates found from Gaia and Hubble? No, actually, in this paper they use both Gaia and Hubble to reduce the uncertainty in the Hubble constant as measured in the local universe. That is to say, the direct measurement that we get from stars in galaxies in our local neighborhood. So the researchers use the power of Hubble to get the brightness of the local stars, the Cepheid, the variables, and they use Gaia to actually have a very precise measurement of the distances to these stars through parallax. And then the discrepancy is between this local measurement and what you get from the cosmic microwave background. So from the cosmic microwave background, you can measure the fluctuations in the temperature, the tiny fluctuations in the temperature in the CMB, and then you can actually fit all your cosmological parameters. And one of those cosmological parameters, of course, from the cosmological model, one of those cosmological parameters is the Hubble constant. And then from that, you know the laws of physics, you know how the universe, or you think you know the laws of physics, or you think you know how the universe is going to evolve with time. So from those initial conditions from the CMB, you are able to produce a prediction of what the local universe, on average, on a statistical level, should look like today. And that is the prediction that is presenting attention. And yeah, we also see this tension from other local measurements of the universe. That those are the measurements that come from gravitational lensing. So the measurement that we have that we're talking about today here is using variable stars in the local universe. but also you might find in the literature that you can use gravitational lensing to get a local measurement of the Hubble constant. You need to combine with other data sets because gravitational lensing alone doesn't tell you like a lot about. With gravitational lensing alone doesn't tell you about the Hubble constant. But if you combine it with other data sets such as supernovae, uh, you also get a value that it's in technical terms is about like 2 or 3 sigma away from what the CMB is telling you, and this is not enough to say that they are completely different, but at the same time, it's pointing towards some tension. So that's why it is important that these measurements that we're reporting today, that they're actually very direct measurements, um, very reliable from variable stars using a data set such as Gaia, so that is very precise and powerful, and it's actually shrinking the error bars and it's telling us the tension is still there. Is it 73? Yes, so I think Hubble, yes, I think these guys get a value, like if you wanna know the exact numbers, the local value that they get from these measurements is about 67 kilometers per second per megaparsec, and the CMB actually gets something about 73. I'm sorry, it's the other way around. The local measurement gives you a measurement of 73.5 kilometers per second per megaparsec for the Hubble constant. That's the local measurement. And the CMB predicts something of about 67 kilometers per second per megaparsec. So 74 to 67. And then you have to start asking yourself about the size of the error bars and the confidence contours around those mean values. But yeah. Um, okay, so we're talking about somebody is asking me in Spanish. Thank you, Reinstro. So yeah, I think here I'm supposed to speak English, and that's okay. But you can ask me in Spanish as well. A cool thing is I'm doing a podcast in Spanish that is going to go on air soonish, hopefully, about cosmology and stuff. But the question in Spanish is, could you talk a little bit more about the probability of detection of this type of neutrinos? So I don't know the exact detection probability, the probability distribution. Yeah, that's something I will have to go up and check. But qualitatively speaking, this is something that we know is very, very tiny. But I think you're looking for a more quantitative answer, and I don't have it right now. And you will have to look at the probability distribution, and it has to do, of course, with the cross section, like so to speak, the size of the neutrinos and the size of the interaction size of the particular ice molecules that they're interacting with, and it's usually involving an expression that involves the size of this particular interaction region which is called the cross section, and the velocity of the particle, and it's like a distribution, and then you do a sum of an integral of that, but I don't know as of now the exact probability for that. So the same person that asks us about this is very interested about the probability, the detection probability of this. And yeah, he's asking in Spanish, and as I said, you guys can ask in Spanish. Right now I can answer in English so everybody can understand, but I mean, if you are interested, you can also send me an email or something, so we can follow up, and I'll be more than happy. Um, so it is very important. Yeah, this is very exciting news. You're gonna see it all over the news. There's a lot of press releases from different sources, and every telescope that was involved in this is probably going to come up with with their own press release. But you can go on YouTube and you can actually watch the a recording of the NSF press release. The Hubble constant has been continually revised as more data comes in. That's true. Yes, throughout the years, even since the time of Hubble, he measured something of about 500 or something. So throughout the years, yes, that's part of the quests, the cosmological quests, the CosmoQuest that we are uh, pursuing, trying to determine the values of the cosmological parameters, and one of them is the Hubble parameter. I believe that IceCube detects individual neutrino events. Yes, that is correct. It's able to identify individual neutrino events, and in particular, these very high energy neutrino events that are just a few or even just a couple of them. With this Blazer announcement have set off all the world's neutrino detectors. That's a good question, and I'm not sure about that because you need to be able to have the technology to detect this type of high energy neutrinos. So the type of neutrinos that are coming from this source are, the point of this is that they're very far away, that they're very high energy. As I said, about 10 times higher than what you can get from the LHC, the Large Hadron Collider. And the Ice Cube is basically designed to detect this type of events. And for that, you need to have this huge amount of material, and then you have to have the particular detectors. Super Kamiokande was able also to detect this type of signals. So I don't know if all neutrino detectors that you have on Earth are actually designed to detect this type of neutrinos in this particular part of their energy distribution. But then on the other hand, the point of this study was that you would expect a signal in different types of in electromagnetic radiation in different type of channels, and that's why we're talking about multi-messenger astronomy. We have the neutrinos, we have the electromagnetic channel, and then recently we also have the gravitational waves channel to know more about the universe. IceCube is directional, that's why we're able to do this. Yes. And the way that Cherenkov radiation gets created, the geometrical form, we're able to identify where they're coming from. So and yeah, an IceCube is directional, so you can tell, oh, there's an event coming from the other side of the Earth. So an event that actually had to go through all of the Earth and come here. But at the same time, we have an event that came from the other side where I don't have Earth. So we're seeing this type of events from different parts of the sky. And one of the cool things that they did today is that they were able to say, most likely, we're going to give up high probability that this event is coming from a small patch of the sky, which was like about, as I said, 1 square degree. I remember a couple of years ago or a year ago when they sent an alert, they sent an email about the gravitational waves, and that there could be an electromagnetic counterpart. I remember like the very first one, it had an area of about hundreds of square degrees, and that was really hard. I think we looked for an electromagnetic counterpart, but of course, like hundreds of square degrees of the sky, that's a lot, and it's very hard to find. Well, the point is that once we have another detector of gravitational waves, for example, the one in India or the one in Italy, then then you can triangulate. So here, in the case of IceCube, actually are able to identify a relatively small region of the sky, and of course that's going to enhance the probability of finding the electromagnetic counterpart. Yes, square degree is still large. You could feel 4 full moons, but it's relatively smaller. That's something doable. As I said, if you have some patience and then you tile um, that region of the sky after several nights, then you are able to do it. Which neutrino detectors are directional and which are not? Is there something like an omnidirectional neutrino detector? I don't know the answer to that question. So I believe IceCube is able to detect in several directions. I don't know if all of them to call it omnidirectional. Um, I do know that there are some detectors that are actually pointing in a particular direction. But there's, for example, the neutrinos that you're sending from them. You have a mine in Canada, and then you have the detector at Fermilab. So then those are actually pointing in that particular direction. So you can try to find they're trying to find neutrino oscillations. But yeah, so that's all I know about that. That was not a criticism about the size of the moon. Yeah, no, that's okay. I didn't take it as a criticism. It's just it's to give us a sense of the size of this. The sky, of course, is very large, and in 1 square degree, as Uncle Bill points out, you could fit 4 full moons, which is relatively small, so to speak. That would be the bottom line. Um, no, yeah, thank you, Guido, for your questions. It's a good topic to talk about, and yeah, maybe I'll do some more research, and next time I'll have a better explanation. Um, all right, everyone. I think it's time to go, but it was a very exciting day. Thank you so much for your comments and your questions. I always have a lot of fun reading about your interesting questions. And yes, thank you so much for watching. And yeah, this has been the Daily Space. It's a production of CosmoQuest, created by the Astronomical Society of the Pacific. And we want to put science in your brain. So thank you very much for following us. And if you like this show, of course, give us a follow, talk about the show with your friends, put it on social media. And yeah, it's a very interesting place to talk about science and discuss amongst ourselves. So I'll see you guys tomorrow at 1 p.m. Eastern Time in the United States, 10 a.m. Pacific Time, and 6 p.m. London. So bye bye, everyone.